Good morning. A little bit longer to get situated here today. How's everyone doing today? So today is our last lecture portion or the instructional lecture. Ready for that? No? I see some of you shaking your heads. That's a good thing. That means you get to finish the semester soon. So if you've already got 12 points of participation, you're not going to get anything extra, right? Today is an extra class, so to speak. So if you miss one class or something, today is one of those chances to make up. Right. We're in our last section. We have Dr. Case coming to speak on Thursday next week. It's Thursday next week, right? Yeah. And Thursday this week, we have your third exam, which will cover up to the content that I did last week. I am going to correct something from last week at the beginning of the lecture today, so that will be included, right? And I'll make this available online today. How many of you have seen the last video that I posted online? Okay, is that helpful? Okay, right. Okay, so we are in biopotentials. What are some of the things you remember from last week? Just shout out a few things that you remember from last week's lecture. Electrodes degrading, we talked about that. Thank you. And how sometimes that shows up as a motion artifact because the electrode might be sliding.
We discussed the electrolyte interface.
We talked about the electrode-electrolyte interface. When I drew the circuit on the board, I think I talked about the skin. I haven't talked about the skin yet. So what I drew earlier was the capacitance was the electrode-electrolyte interface. I'll verify that today once we cut to that. She did not request a Zoom. Okay, yeah. Anything else?
We talked about the difference between voltaic and electrolytic cells. So like the voltaic cell, there's like a chemical reaction that like creates electricity, while like electrolytic cells, you have like an external power source, and that's driving like a chemical reaction.
Yeah, we talked about voltaic and electrolytic cells, half cell potentials. Anything else you remember? Okay, so today we're basically going to be doing the last two. The last one is really just more like here are stuff. We talked about oxidation and reduction. Remember that? So remember those things. What's oxidation and what's reduction?
Oxidation is the loss of an electron versus reduction. I can't say today. Reduction is the gain.
Okay. And then I think, where did we stop? Talked about these, talked about half cell potentials. I think I showed a video at some point, a long video. Oh, and the overpotential or the total potential, I talked about that as a half cell potential, plus the sum of all of these potentials due to the resistance, the concentration, and the activation. And then we did the motion artifacts, and I think this is where we stopped. Okay. So here, I think I made a mistake here when I was talking about, I was going to the next section. When you have, let me draw it on this. when you have an electrode on the electrolytic surface and the skin. So here at this surface, the capacitance of this interface and the resistance of this interface is what we do here. Right? So we haven't come to the skin yet, but here at this surface, you have some kind of capacitance because you have the electrolytic interface. So that capacitance is what's given here. And then that resistance is what's given here. The half cell potential due to the actual electrode, that's what's here. And then whatever material you have here as your gel or the electrolyte, that's what you have here. Does that make sense? Okay. So this is still from last week. So based on this, just talk to the person next to you and can you draw the circuit for two of these? If you have two electrodes, the skin, because we haven't spoken about the skin, just do the skin as one resistor. Don't consider the capacitance or anything. Just do the skin as one resistor. And each of these electrodes will have a half cell potential. You can call it E1 and E2. Yeah, so draw this. Talk to the person next to you. You have the slides on Canvas, right? No? Oh, okay. Okay, while you do that, I'm gonna quickly see if I can get the Zoom link. Yeah. Okay, so hopefully, okay, let's come back. What it would look like is basically the same thing twice. This part I talked about. Right. Where would your skin be? On the right side, sorry, on the left side or the right side? Why would it be the left? See, if I drew this is why I wanted to explain this again, because I realized even though I drew it on the board and I talked about the skin. So this potential is like that. And then you have this. Then you have the resistance due to the electrolyte. Where would the skin be? So the skin would be here, right? So we would connect this with, we would connect this like that. And here you have the half potentials. So your potential difference would be through here, E at C minus this one. So in the textbook, this, I think, is drawn here. So in the textbook, erase some of this. They've taken this and put it here. And then turned it up sideways, which is the figure that I have here.
So you're saying that the EA and EB could still be on the other side?
It doesn't matter. So when you have, oops. When you have something like this, right? If you're only considering from this point to this point, it doesn't matter which order it is in. The polarity matters, but the order doesn't matter. So that's what you see in this diagram, right? The polarity cannot be reversed, but in the earlier diagram, this was here. If I asked you to do a calculation, the voltage here and voltage here, now that would be different from this and this. But if you're just considering the potentials or the entire potential, that doesn't matter. Oh. Okay. Right, any other questions? Yep. This is how it's given. So if you look at the next one, next diagram, basically they have the resistances here. So if you look at, I have given the reference for the textbook at the bottom. I'm not sure why they gave it like this, because in the right next diagram, it's reversed again and given like this. So since I copied it from the textbook, I copied it like that. And I didn't even think about it when I drew it. And then when I went to, I was like, wait, I was doing your exam question. So yes, it will come for the exam. And that's when I realized, oh, yes.
Question for the diagram, there's the one that you drew or the picture one. Could you explain this to clarify why the half cell potential is the difference between the two different E's? Just so that I
No,
understand.
the individual half cell potential is the E. So each of these represent the half cell potential. When you consider the potential difference between the two, you're looking at the voltage or the potential difference, then you do the half cell, the difference between the two half cell potentials. And if you remember from last week, one of these might be positive, one of these might be negative. So then you're really adding the half cell potentials, if that's the case. Any other questions? Okay. So then we're going to add the skin to it. You have different layers of the human skin. What are the layers? In a very high level overview. Actually, I have a lot of time today because we're going to finish this in 15 minutes and then just go over what we've done the entire semester. So why don't I again have you break up into pairs and just look at each of these layers of the skin and what they do, what's going on in each of the layers. I'll give you like 3 minutes for that. And for those online, you can type in. So the epidermis, dermis, and the hypodermis, what are they? What's going on in each of those? Since we only have one person online, you can just type in the chat, whatever you find. Okay, right. Let's discuss. Let's take with this group since you have the mic. Talk about the epidermis, and then we can keep going down this side.
We found that it's pretty much like the first phase is what is constantly radiation of the first layer of protection for the skin for protecting us in germs and
Okay. Next layer.
yeah, so the dermis is kind of where the second layer, that pink layer you see there. It holds a lot of glands and nerves and also has like capillaries.
Okay.
Then hypodermis is the deepest layer, and it's mainly composed of fat. And so it just kind of anchors the skin to the muscles and bones and acts as a shock absorber for protection.
Okay. So each of these layers, if we want to go down, how many of you have taken some kind of physiological modeling class? Right? Have you studied or learned how to model different parts of the human body with either different circuits, mechanical circuits? Maybe?
PE class, so it's like biological circuits kind of, but so somewhat, yes.
Okay.
It's not like super in depth. It's not like practical, like we don't actually do a lot of learning and not a lot of doing.
Yes. There's a lot of learning required before you start. Thank you for that. Before you start doing, so what I wanted to share is, so you have different layers and you can make it as complicated as you want. But to start off, since you've never seen any of these, the skin is going, so we have, so up to now, we have the half cell potential of the electrode. Then you have the electrode-electrolyte interface. Then you have the gel resistance. That's what we have done up to now. The epidermis, we're going to do with a capacitor and a resistor. And this in between, this is where basically your ions are going to be going in and out. So the potential due to that is modeled here. Your epidermis, you have a capacitor and a resistor, and everything beyond that, basically modeled with a resistor. So that's one line. Then also, inside these things, you have sweat glands and different ducts and capillaries and whatnot. You can also add those over here, right? I can keep adding things for every different component that you find in the body, which would make things complicated. Given that this is an introductory class, this is where the textbook basically takes you. If you take, I don't know, 8,000 level systems modeling or something like that, you might end up doing further modeling. Have you done any of this in medical school? No, okay. So maybe EE, I would think the 8,000, I would think there would be a 3,000 or a 5,000 level class before you get to the 8,000 class, but maybe not. Right, did you have a question?
It's just a clarification question. So, I remember when we were doing bioimpedance lecture on how he had specified that fat has the highest impedance
Yeah.
level, if I remember correctly. So I'm curious on since the well, it says dermis, but since the dermis and subcutaneous layer.
All of these are
Yeah,
just junk.
Yeah, since that's composed of fat and muscle beneath that, I'm just curious on from a practicality standpoint, why is it just labeled with a resistor when technically speaking that has the highest impedance?
Because we're not going anything deeper. So if you look at the previous one, see how this one was just one resistor for all those layers? So it's basically taking you one level deeper every single time. So if I were to take you even further, then we would start modeling these with other components, right? I know this is not a lot. It's like, oh, here's what it is, and I'm not showing you any kind of practical application of this, but this is kind of where we stop with bioelectrodes, just because there's so much of content in the course. So please know this, know what each of these components are. And if you remember exam 2, I'll come back to you. Exam 2, I had given you a hypothetical circuit from a hypothetical planet. I could do something similar to that because I really can't ask you to do a lot of calculations in these. There was a question all the way at the back. Yes. So all of that, sorry, all of that at this level, we'll model with this resistor. So epidermis gets modeled with the sweat glands and epidermis. All of the rest gets modeled with a resistor at this level, and I'm not gonna teach you or ask you questions on anything deeper than that. There's a reason for that too, that I will connect back to the very first lesson. Can you remember we had okay, this is a human leg. We had how transverse and longitudinal, remember that when we did electrical safety? So some of these might be superficial. It might not go all the way to the deeper layers. So in that case, this is justified. So you just have just the superficial layers, the resistance of the superficial layers. Okay, then we have the very final group work we're going to do for the class, which will put us to the rest of it. Basically looking at different micro electrodes and stimulating electrodes. These come in all shapes and sizes, all different types of materials. What I want you to do is, let's do this. Get into groups. And now this is a little bit tricky because I want each of the groups to explain something different. But the question is, what are the different types of electrodes used? So I have given you a whole list. If you want, you can pick one of them. If you go online and search, you can just find one. Only thing is, you cannot do something that another group has done. So you might need to search a couple of them. Right? So what are the different types of electrodes used? Like how do they work? And examples from biomedical engineering where it's used. So yes, I want you to look at more than one, but I only want you to report one. I'll give you about 5 minutes for that. And with that, we end the class. No, sorry, with that, we end this section. Okay, oops. Right, who wants? That's weird. Okay. Who wants to start? Who has the mic? I guess the winner. Okay. That's the easier one.
So we chose loading electrodes, and basically what they are is a standard metal plate electrode, but they're recessed into a cavity of usually gel, which using doing that will any sort of motion or artifact that's caused by the subject would be absorbed by the gel instead of the electrode, so that the signal will remain clear, and then that can be used for a number of things.
Okay, next group. Oh, biomedical application, sorry.
How was the security what we've been doing with gel separates it. And it reduces noise from the motion and moisture of the patient, so they're really useful for applications like that.
Next group.
We looked at the fabric dry electrode. So these are flexible wearable sensors that are made from interactive textile material. And they can measure bioelectrical signals, ECG, EMG.
Good.
We looked at the micropipette electrode. This is like a submicron tip filled with electrolyte solution that detects bioelectric potential at a singular cell level. And its applications include.
Like interested in recording pattern, single cell electrophysiology for measuring potentials. But the limitation is that it's part because of the size, it's pretty far down and only used in plastic and things.
Okay. pass it on? Or you have more to add?
We look at, internal electrodes, and these are electrodes that bypass the skin layer. And therefore, the skin is impedance. Typically, they're needle electrodes, there are also, wires and, implantable, versions, and they're typically used, in implantables and, a lot of neural interfaces, such as deep brain stimulation and brain interfaces. We all about that just a few weeks ago, how the patient looks and how those electrodes swim to the tissue of the heart.
Did you specifically look at needle electrodes for all those applications? Okay, I was not aware of it, of needle electrodes being used that way, but okay.
We looked at electrorays, which is basically machine multiple electrodes,
Mhm.
specific geometric pattern, superficial patterns. And it's used in PBS, for Parkinson's or essential tremor, and also key powders.
So the micropipettes, which you use to the people that are something themselves.
Was there anything else you looked at? All of them are taken already? Okay.
So, I mean, I was gonna ask a question, is a percutaneous different than a needle electrode? Because they seem very similar in size.
It goes in the skin.
Yeah, but
Yeah.
it seems to be slightly different than the juice lamp. Rather than,
Yeah, so one you measure nerve activity from the nerve, and the other one is more like from a pool.
people's electrode, which is a small wire that's it's like screwed into the baby's scalp during labor, and it's used to monitor heart rate.
One of the things that this might be the case, I'm not sure. Usually, this is from, because I guess 3 different groups talked about it. When it goes to deep brain stimulation, you have electrodes that are slightly bigger than a needle electrode going in. So, but maybe they do use even smaller ones now. Okay, we have a few more groups to go.
Flexible electrodes, and it's a thin adaptable electrode that is made by depositing the metallic onto flexible substrate.
These are commonly used in like soft robotics and studies, as well as ECG, EMG, and EEG monitoring to reduce noise.
Okay, I looked at the capacitive or the non-contact electrodes. They work, through like a thin layer of insulation. Even if you're wearing a shirt or a car seat, they're used in like a smart bed, monitoring. So if you're trying to diagnose someone with like sleep apnea, you can be there, with them through the pajamas with the clothes of the morning.
We looked at stimulating electrodes. So stimulating electrodes actually deliver current to the body in order to treat various conditions or function system.
Obviously, examples are looking for stimulation, but also like cochlear implants and like auditory nerve by sending current to the nerve to stimulate it, and then there's also a physical therapy option, something called TENS, which is transcutaneous electrical nerve stimulation. That's used to like relieve pain.
We all looked at average drawing, but one of the options.
What was it?
Average drawing.
Okay.
It's stated, one of the options were metal plate electrics as well. I looked at it too closely, but I know some applications that are like, EKG to monitor that heart muscle. So that typically it deals with like ionic current and electric current. But one application would be like, EKG, like muscle activity monitoring, once you take those.
Okay.
Yeah.
Yeah, thank you. I don't have time to go into depth about how like the impedances for each of these will change, like what you're recording. How many of you do biomaterials concentration? Oh, nobody. Oh, okay. So I was going to say, if you do, have you taken biomaterials classes? Have you learned this in biomaterials classes, perhaps? No. Okay, some are saying yes, some are saying no. But if you do advanced biomaterials classes, you will learn more about how the electrode, electrolytic, and like the surface of whatever you're recording, like in this case, the skin, it could be nerve endings, how those interactions, like at a molecular level, happen. And unfortunately, this is all the time we have for this class. And I also see, I think you just took, oh, we didn't give you guys a chance. Yeah.
Guess you could add more about the metal plate
Okay.
So I got to what you just said, like, one of the advantages is that it has high productivity, but and you can like reuse it, but then it has like high skin impedance. You actually need to like add like a conductive case to maintain contact with the skin. It also like degrades too. Another application is that it's used to simulate signals, so it's actually used for like as like a paddle in defibrillators.
Okay. You might see in TV shows, they might show like the paddle electrodes going into the heart, open heart, and they deliver current versus the external defibrillators that we talked about. Coming to, so I guess metal versus dry electrodes, they're also metal. In EEG applications, one of the things is you can have those gels. More of the modern technology is to go for dry electrodes, but they don't last as, they're not, I shouldn't say they're not as good, but practically so far, the ones with the gel actually outperform on longer recordings. The in-between is, so I'm just going to draw something here. You have gel here. Instead of the gel, you can also have just dry contact. You'll have like a gold-plated or a gold electrode. In between, something you can have is just put a salt solution here, so what's the disadvantage of having EEG with gel electrodes or metal electrodes that need a gel layer? Did I talk about this in the EEG lecture? Since I didn't redo that one, I don't remember. So once you connect this, you're good, you're solid. But if you have like another electrode here, and this gel goes all the way, this is what we call the webbing effect. Basically, instead of getting two different signals, now you basically short-circuited this. This doesn't quite happen in gel electrodes. So gel electrodes, if you want to take a recording for like 2-3 hours, the space is pretty good. You stick the electrode and for 2-3 hours, this gives solid recordings. With dry electrodes, if you're doing a 10-minute recording, this setup might actually take about 20-30 minutes. So if your recordings are really short, this might be beneficial, just thinking about the time. The in-between is you can have the electrodes and you can inject a salt solution into it. Then there is a higher risk of having that webbing effect, unfortunately, because if you put too much salt, you're going to have the entire area concentrated. This is kind of an in-between because after about 45 minutes to an hour, you might have to wet the electrodes again because it's like a salt solution. Just something, since we're talking about EEGs. Okay, so this brings us to the end. Please read the reference text. How many of you have, I think all of you should have access to coursework. Right. So the rest of the time, what I thought we'd do is, let's see, just go over some of the things we've been talking about throughout the semester, and I'll give you a chance to like clarify anything. And then I've also put up 2 circuits on the board that I'll give you time to do. And we'll talk a little bit about the extra credit. So if you want to go back, look at your notes. I'm also going to do the same thing. Lesson 1. Who has the mic? And we can pass the mic along again. So we had 6 lessons, not counting the introduction. Lesson 2, we talked about circuits and electronics. We talked about just how electricity flows. What are some of the things you learned in this? The reason I'm going back to the basics is last week I found out that maybe some of you have a little bit of confusion how electricity works, voltage versus current. So what are some of the things you remember from this lesson? KCL, KVL. How do you apply KCL, KVL? Oh, do it here. Little bit louder or get a mic. Pass it down. Mic is off. If it's red, it's off. Thank you.
PDL is a match. The accumulation of current, the accumulation of voltages is 0.
So if you take, thank you. If you take 1 point, usually I take the bottom left. You start here and start adding all of the voltages across all of the components and come back. The sum of all of that is how much? 0, right? KCL.
The current going into node versus the current leaving the node sums up to 0.
So if you have currents coming in or out, so in this case, you have 4 currents coming in, I1, I2, I3, I4 equals 0, which means some of this, the direction, you'll get a negative answer and you'll reverse the direction. I'm trying to remember. I'll come back. Actually, maybe this is a good time to talk about that here. Oh, and I don't have colors today. If you consider a place like this, right? Actually, I have that, I think, all the way at the bottom. I'll upload these slides afterwards. So if you consider a node like this, a place like this V1, if this is V2 and V0 or V0, what can you say about V1, V2, V3? Yep. It's the same voltage, it's the same point. If there's no component in between, if it's just connected by a wire, all of this have the same voltage. So everything that I'm drawing here right now has the same voltage. Anything else here, all of this, same voltage. Anytime, and for some of you, you might be like, why are you explaining this again? That's okay. Anytime a current flows, you have a current flowing and then you have a node and the current separates, then you have current going in different paths. In this case, how much is this current? Why? Why? I'm just making you answer more. Because of the ideal op-amp assumption, input impedance is infinite, so there's no current flowing in, which means this voltage is this, which means all of this has the same voltage. Here, if I call VA as the red voltage and VB as the blue voltage, what's causing VA to become VB? What's causing that? What's the reason for that voltage drop? A little bit louder. The resistor, right? The current which is flowing through the resistor, any kind of component you have will drop the voltage, right? When I say drop the voltage, depending on which direction you put the current, it might increase or decrease. But anytime you have a component, your voltage will drop. And that voltage difference is the potential here minus the potential here. So VA minus VB is the potential difference or the voltage, same thing, across your resistor, which is proportional to the current flowing through that resistor. And the constant is called the resistance of that component or the resistor, right? So what do we call this law? Thank you. So that comes, we have a KVL, KCL, Ohm's law, and we learned one more thing. We did, yeah. The voltage divider. If you have something like this, the voltage here, if you know the voltage of the entire thing, if it's a resistor, it's proportional to this resistor versus this resistance. So if this is R1 and R2, how much is this? If this is V, what would the voltage here be? So proportionally, the fraction of the resistance here is R2 divided by the entire resistance, right? Thank you. Times this, your voltage. So if you know these four things, am I missing anything else? You should, in theory, be able to do circuits, but in practice, you would have need to done quite a bit. Then we talked about, we started with active and passive components, analog versus digital. You might remember those. Okay. Then we did the Wheatstone bridge. What's the thing about the specialty about the Wheatstone bridge?
It enables you to, if you know the resistance of three of the four, you can calculate the fourths, and
Yep.
we were just talking about in our later section that is used a lot in sensors. I'm trying to remember which one is specific.
Several sensors, but I think the example I had given was from temperature sensors, right? So even though Wheatstone Bridge we talked about in the earlier section, for the exam 3 section, we again talked about it. So if you only learn temperature sensors and not Wheatstone Bridge, you might be disappointed. We talked about impedance, how the total impedance is a sum of all of the different impedances, a resistive, inductive, and capacitive. We talked about some of them only have resistance, some of them have reactance, some of them have both. We talked about loading circuits. This one is actually finding the input impedance, but I just as well can give you a question about the output impedance. We talked about a few examples with diodes, electrical safety and grounding, why grounding is needed. I think there were 2 videos I had shown about how when you have grounding loops, you have more noise. The transversal versus longitudinal, I talked about it in this class also, how to model those. Different current levels and the physiological effects of each of those. And then I think finally we talked about isolation transformers and the purpose of that. Any questions from this section that you would like me to go through? Okay. And then we went into instrumentation. What are some of the things we learned here? What are the things you remember in this?
First and second order systems.
First and second order systems. Linear time invariant LTI systems. Remember when the switch gets put, what's going to happen? So the extra credit, it'll be a half an hour paper, so to speak. I will cover both sections sections 3 and 4. So this section and the op amps section. I'll talk about that at the end of this. What are some of the others you remember in instrumentation? It's fine if you go back to those notes. I'm also doing the same thing. Laplace transforms, Z transforms, different characteristics, static and dynamic characteristics, and most of these were dynamic, but we talked about the different characteristics and how to measure each of them. Oh, and we talked about stability, the pole zero plots and Bode plots. Impulse response, I talked about the impulse response, step response, and that comes into the natural response and the forced response. Then with amplifiers, I feel like this I've gone through quite a few times. We talked about the different configurations. So ideal op amp, ideal versus real. Then we talked about the limitations in designing how we would change the ideal assumptions into real. How we'll only consider one of the parameters, we won't change everything to real. And recognizing the different configurations, right? So these were the most commonly used configurations. If you can identify them and use the equation correctly, I have no problem with that. But all of the students who got it wrong, they got it wrong because they just memorized and applied it. You do need to be able to identify different op amps, but don't rely on that. If you can work it out from first principles, that's okay. And with op amps, we get to convert the passive filter into an active filter by adding an op amp. So for the extra credit, I know some of you cannot make it to office hours on Thursdays, so I'm trying to see if I can arrange a different time. Right now, what I have is next Thursday during office hours. It'll be half an hour. I'll post if it's like 3% extra credit or 5% or somewhere in between, so 4%. So it's not going to be more than 5%. It's mainly meant for students who really want to go from a C to a B or a B to an A. The questions will be harder because I really want to, yeah, you have to show me that it's justified to give you extra credit to jump up a grade. The content will be from this op amp section and instrumentation section. And I know there are only 2 students in class who have an accommodation for a separate room. So if you do want to take the extra credit class, please come and talk to me today so that I can find a different room for you. Or we can work out something. And I do believe the others who have accommodation just have extra time. So you'll be in the same room as everyone else. Any questions about that? Then we did, so these were after the mid-semester break, so hopefully it's fresh in your mind. We did different kinds of sensors. The displacement, I think the resistive we had done quite a bit. And then we did temperature sensors, did some calculations, and then optical measurements. I think I got something stuck in my throat as I was coming to class. We also talked about how to measure performances and the characteristics, which kind of connected that lesson back to the instrumentation lecture. There were pressure measurements, which I said for this year, I will not include that in the syllabus. And then we had biopotentials. We talked about just the basics. How does action potentials work? What does a neuron look like? What are the different parts? Sodium, potassium pump, resting membrane potential, how the synapse transmits the neurotransmitters. And we looked at 2 basic tools that we use to calculate different things related to biopotentials. Strength duration curves, patch clamp, and the Hodgkin-Huxley model. For the Hodgkin-Huxley model, we did the circuit, we did some derivations just for one type of ion. So for the exam, I can't make you derive the entire thing because that would be way too long. But I could ask you sections. Like, here's a hypothetical planet, which is what I had given you for that exam. I could ask you about the subunits. What can you tell me about the subunits? How does the math work for the subunits? Then we also did ECG and EEG for that section. So know how to calculate the heart rate from ECGs. What are the different arrhythmias? How do you recognize those? If I asked you to draw an arrhythmia, you should be able to draw it. What are the other things? The different leads of the measurement system. EEG, again, now I think this we talked about a little today also. The different spatial temporal scales of neural signals, the time and the resolution. And then finally, the last section that we talked about today, which we went through already. Right, we do have 10 minutes. Oh, and then the exam 4 is cumulative. It's still 1 hour. Given that I need to test you on the entire content, I will have a lot of multiple choice. So read and just pick A, B, C, D, one of them. Some of them might be short answers, and you might still have circuits and problems to resolve. There'll also be questions from guest lectures. I think 2 of the guest lectures are online. 3rd one is not. Sorry about that. 4th one, it depends. If she says, okay, I can share it online. Then the student presentations, I haven't uploaded the schedule, but I think the first 5 groups will be the first week, and the next 5 groups will be the second week. You'll have questions from the student presentations. I'm not going to go into depth, but just basic questions that if you actually pay attention, you should be fine. And so the next 10 minutes, I'm going to give you these 2 questions. Feel free to get into groups of 2 or 3 and do these. Actually, maybe do it on your own and then compare with your neighbor. Yes. The other groups. Yeah. I will upload because there were 2 groups that had issues, I think. So I want to confirm that the students in 2 groups, one of them I checked, the other one I haven't checked. I'll post it online. And then I'll also post these slides as soon as we're done today. Last week, I noticed that some of you had not signed the sheet, but because you did talk, I emailed you like, hey, I kind of need to verify that you were actually in class. Next time, make sure you sign. So I do see the sign up sheet up front. If you haven't signed, just raise your hands. Oh, there you go. Okay. Could you pass it to the back? And if any of you have finished this, feel free to come up and do the problem. Or maybe I will do it in the interest of time. Mhm. Okay, let me clarify something. Thank you for pointing it out to your classmate. Okay, this figure, just completely erase this and this, right? And just put the resistor, the half cell, oops, and put the half cell here, right? Hopefully that will make it clearer consistent with the previous slide. So the previous slide has it like that. Draw it like this. Maybe it was a mistake in the textbook. Because the reason for that is the voltage, which your classmate actually just asked me a question and I realized you're looking at the two half-cell potentials here and here due to these two. So if you have it here, that doesn't make sense. So yeah, just erase this and this. Any questions about these two? For those of you who did the exam last time, I'm going to give the answers for these two. Oh, sorry. Wrong thing. So the first one, what are the answers you got? One milliamp, anyone got that? Yep. And this is how much? 7 volts, thank you. And Vs over Is, input impedance. R1 plus R2 plus R1, R3 over R2. Last week, I went through this problem with some of you. Some of you kind of got lost in the math. It's still, yes, we have a math, heavy math class, given it's an advanced engineering course. If you have issues reducing this down to a simple form like this, or got lost in the math, we can talk about it. But otherwise, good luck. I will see you at the exam on Thursday.